Okay, thank you very much, Joyce, and thank you for the chance to talk here today. I'm going to be doing my best to represent the projects underneath the ENKI umbrella. Um, it's quite a wide range of projects, some of which I'm familiar with, some of which I'm less familiar with. And the names I added here were just the people I spoke to about this presentation, but some of those projects involve developers who I haven't listed here. I've tried to add them to various slides. But at its core, what ENKI is, or at least the part of ENKI that I'm going to talk about, is the use of symbolic representation of thermodynamics and subsequent code generation of thermodynamic libraries that we can use in either thermodynamics applications or coupled to geodynamic problems. And because I'm a geodynamicist, I always like to start this with a sort of motivation from geodynamics, where these sort of symbolic representations of problems have been around for at least the last decade, if not longer now, and have really progressed from being able to do problems where we just reproduce simple benchmarks into sort of more scientific applications, and more recently into sort of quite large scale geodynamic simulations. Um, and what all of these examples have in common is that they're using a sort of symbolic representation of the problem, which is then using code generation to generate fast, consistent code to run the actual simulation. And there are a number of numerical libraries out there that do this. And which one you choose probably depends on which discretization scheme you're interested in using. But I'm going to be relying today on finite elements and the FEniCS project. And for those of you not familiar with it, I'm just going to give a quick example of using FEniCS. So if we have a description on a piece of paper of a partial differential equation that we want to solve, in this case, a Poisson equation in some domain with some specified boundary conditions, we're going to want to solve that using finite elements here. So we're going to multiply it by a test function and formulate its weak form, and we're going to solve this form of the equations. What FEniCS allows us to do is to describe that in a very short Python script. And I'm not going to go into detail on this Python script, but what you'll see is that we have just a description of the domain, a description of the boundary conditions, setting up our test function that we're going to multiply our equations by, setting up our right-hand side functions from our equation. And then, most importantly here, we have this two-line symbolic description of the equations we want to solve. And we're going to pass that symbolic description of those equations into a solver, and we're going to get our solution back. And that symbolic description is doing a lot of work. In the background, FEniCS is using that to generate hundreds of lines of code that actually give you the finite element assembly code for this problem that we're solving. And this is obviously very convenient for users and developers, but where it really comes into its own is on more nonlinear problems. So here, this is just an example of incompressible thermal convection, where we have coupling both between the equations and, depending on the rheological model, possible nonlinearities within the momentum equation itself. So we could solve this, for example, using a Newton iteration, where we're going to have a residual that we want to find the root of, and we're going to have the Jacobian of that residual using that to update our solution vector. So we again write the weak forms of our residual. So this integral form down here, and the Jacobian, this J, is just going to be the derivative of that residual with respect to our solution variables. And just like we saw in the previous example, we can describe that symbolically using FEniCS in just 3 or 4 lines of Python. But the real power here is, because that is a symbolic representation of the residual, we can just request that we take the derivative of that residual, and FEniCS will form our Jacobian for us. And again, it will go away and generate the code in the background that's going to do that finite element assembly. And this is very useful, not just because it's convenient, but because it saves us from having to derive these often complex Jacobian forms ourselves, and also saves us from introducing typos into coding these equations up. So the same principle can be applied to thermodynamics. So if we have a symbolic representation of, in this case, a Gibbs free energy, we can use symbolic differentiation to generate analytic expressions for the thermodynamic parameters that we are interested in, and also potentially the higher derivatives of those thermodynamic parameters for use in our Newton solvers, for use in that Jacobian matrix that I was showing you on the previous slide. So that is what ENKI is trying to use at its core. And I would encourage you to visit the website at enkiportal.org and also to see the range of projects that are underneath this ENKI umbrella at the GitLab page for ENKI. But at the core of ENKI is a Python module called coder.py, which is using sympy, symbolic Python, to input symbolic representations of the free energies for thermodynamic components and phases. And then it is using automatic C code generation for the thermodynamic parameters. So building up a thermodynamic database in Coder looks a lot like Bob's slide on this. In fact, I think we use some of the same Wikipedia pictures of these minerals. So we start with pure composition and members and species. And we go to the literature, and in this case, we look at Lars and Carolina's 2011 paper, and we want to implement this free energy model for these end members. And on the left, I have a screenshot of a Jupyter notebook that has imported Coder, is using Coder, and it's using sympy. And we can see the sort of one-to-one correlation between the equations in the paper and the equations represented in sympy in our Jupyter notebook. And we can build that up until eventually we have a full representation of the free energy model of this component. And just like Bob was showing, we then take those components, build them into these multi-component phases, and again, go back to the literature, have another Jupyter notebook, and pull out the symbolic representation of our Gibbs free energy of the thermodynamic phase. So now we have this symbolic representation of our Gibbs free energy. And like I said before, we can automatically symbolically differentiate for analytic expressions for the various thermodynamic parameters. And just like in the FEniCS example that I showed, what this then is going to do is to go away and generate hundreds of lines of C code that implement the thermodynamic parameters that we want to use in our geodynamic models. And again, this is more than just convenience. This is like a robustness thing. We don't introduce typos when we're implementing all these different thermodynamic parameters, and we're ensuring consistency between our thermodynamic parameters and the free energy model. But then we come to the issue of how we actually couple. So I've shown you sort of a geodynamic example and a thermodynamic example of using symbolic representation and code generation. But these are both sort of high dimensional problems, but they're high dimensional in different ways. So geodynamic problems are interested in velocities, pressures, temperatures, other variables over space and time and their gradients. And because they vary in space, once we discretize this problem, this is a large dimensional problem because of all the points in space we're interested in solving these equations at. Thermodynamics, on the other hand, or a pure thermodynamic problem, is typically, and I'm simplifying a bit here, only interested sort of in a single spatial point, but its complexity or its high dimensionality comes from its compositional dependence of these free energies and thermodynamic parameters that I was setting up in the previous slides. So the two end member approaches to coupling these are a sort of equilibrium approach, where we perform free energy minimization to collapse the sort of the compositional complexity of the thermodynamics into a space that we can use in the geodynamic models through a variety of approaches, either lookup tables or direct calculations. The other approach is to preserve the full compositional complexity of the thermodynamics and instead track the compositions in both space and time in our geodynamic models and use a reactive disequilibrium approach, in which case we obviously have to add equations to our geodynamic models, and we're essentially shifting the expense of that free energy minimization into the expense of solving these extra equations and also resolving the reactive timescales of the disequilibrium processes that we're modeling. So that sort of two end-member approach is reflected in the sort of universe of ENKI software, where things are rooted in using this coder.py module, but equilibrium models are handled by a piece of software called ThermoEngine, and disequilibrium models are handled by a piece of software called ThermoCodegen. And I'm going to briefly discuss them both, but I should say that the developers are working to maintain compatibility between these and increase compatibility between these sort of two different approaches. So we hope to see a world where these are sort of brought back together eventually. So just starting out on the equilibrium side of things with ThermoEngine. Now this is work, primary developers are Aaron Wolf, Simon Matthews, Suzanne Berner, and Marc Ghiorso. I know less about this, so I would encourage you to go and read the docs at the Read the Docs website. And also point out that ThermoEngine is now pip installable. So this is easy to install on your local machine and try out. Like I said, it's rooted in coder.py in this symbolic representation of the thermodynamic databases. And what ThermoEngine brings together is coder-generated thermodynamic databases into a compiled library, compiled and then brought back into Python using Cython. And it couples those with equilibration tools and calibration tools and exposes them to users through an interface known as MagmaForge. There's also an extended universe of ThermoEngine derived and related software packages that use parts of these tools. So for example, Vesical, VaporRock, and Paiju use components from ThermoEngine. And so these are some slides that Aaron gave me to sort of discuss the principal parts of ThermoEngine. So this is an example using MagmaForge to expose in a sort of simple Pythonic way the interface to this thermodynamic library that ThermoEngine has built up through Coder. And this is an example of doing a crystallization calculation for a Moore composition listed here. So that's at the sort of user side of things, but under the hood, there's been the ThermoEngine devs have been working a lot on improving the robustness of the underlying algorithms. So previous versions of Melts and ThermoEngine had issues with breakdown of solvers either in the equilibrium solve, the free energy minimization, or within the solutions for complex phases, the speciation solutions. And they put a lot of effort into removing these cases of sort of unexpected failure, and more recent versions have solved a lot of these issues. They're also interested and working on propagating Bayesian uncertainties through their models so that model robustness can be assessed. And these are a couple of examples of basalt fractionation and mantle melting, where you see instead of a single calculation, they now have a suite of different models drawn from those uncertainties. And underlying all of this, within the thermodynamic sort of database and library level of ThermoEngine, Aaron and Marc Ghiorso are working on calibrating and developing the next generation of MELTS database, MELTS 2.0, which is going to capture a full space of crystallizing assemblages and also provide those Bayesian uncertainties for all modeling applications that we saw on the previous slide. And if you're interested in knowing more about the sort of ThermoEngine side of ENKI, I'd encourage you to reach out to Aaron, and I'll give details at the end about how to do that. So everything I just showed was still a sort of a thermodynamic calculation, was still over here. And we can use those tools of ThermoEngine to generate sort of equilibrium assemblages and to couple using sort of traditional lookup table approaches, for example, into our geodynamic models. But I'm more interested in the sort of disequilibrium side of this, the reactive disequilibrium models. So I'd like to look at what changes in our geodynamic model when we're interested in approaching this from a disequilibrium perspective. So it's mostly changing our conservation of mass equations. Our global conservation of mass equation remains unchanged, as you'd expect. But we have to add to that conservation of mass equations that track the masses of the phases for each phase, and also track the masses of the end members of the components of those phases for each component of each phase. So you begin to see why, obviously, the flexibility of the symbolic representation is useful in the thermodynamics, but it's also very useful to have on the geodynamic side of things as we're adding more equations and trying to come up with a solution algorithm that works for these coupled systems. And we're closing these with reactive mass transfer rates that have to sum globally to zero and are constrained by the second law of thermodynamics, as laid out by de Groot-Mazur and Rudge et al., and also Lucy Tweed's PhD thesis, amongst many, many others. But ultimately, our reactive mass transfer rates end up being related to our chemical potentials through the affinities. And so we're closing our model with we're closing our geodynamic model here with the derivatives of those free energies that we coded up using coder symbolically. So this is handled in the ENKI universe by ThermoCodegen. So how does ThermoCodegen modify a workflow compared to ThermoEngine? Well, or compared to coder in general. So we start with that sort of thermodynamic database that we built up symbolically in those Jupyter notebooks for the end members and the phases. And we add on top of that a symbolic representation of the reaction kinetics for the reactions that we're interested in modeling in our simulation. And again, I encourage you to go and look at the documentation for ThermoCodegen at this link on the ENKI portal. And there is also a JOSS paper describing ThermoCodegen that's available. But again, it's rooted in coder, but the workflow is slightly different to ThermoEngine. So ThermoCodegen is adding a layer of reaction kinetics to what coder is providing. And it's also doing some sort of geodynamics interfacing. So this is primarily worried about translating from mass fractions into moles and mole fractions, but also more challengingly, translating from derivatives with respect to those mass fractions into derivatives with respect to the moles in the thermodynamic databases. And then rather than building up a library of thermodynamic databases, ThermoCodegen generates an application-specific thermodynamic library, which has both C++ and Python interfaces to it. And we couple that with some representation of our differential equations, for example, using FEniCS, to generate a coupled model either in C++ or Python. And I'd like to use my last few minutes really just to give a couple of examples of using ThermoCodegen in this sort of reactive disequilibrium approach. So the first is by Mitchell Macmillan, looking at ecliptization and crustal foundering. So Mitchell was interested in looking at the path of a granulite as the lithosphere thickened along a temperature pressure path. So this is still a zero-dimensional in terms of space problem. So the differential equations that we're coupling the thermodynamic database to here are ordinary differential equations. And the thermodynamic database is Stixrud and Lithgow-Bertoloni in 2021. And those differential equations that database is coupled to introduce a reaction rate. And more importantly, they introduce a relative rate of reaction to transport in our model, to movement down this geotherm. And that leads to a Damkohler number, the relative rate between the reaction and the transport. And Mitchell used that as a proxy and calibrated it to observations and experiments on ecliptization and generated a range of possible Damkohler numbers from really quite low values, sort of like 15 up to 10 to the 6, depending on whether there is free fluid present in the system. And so what Mitchell showed or modeled here using ThermoCodegen is depending on the pressure temperature path that you take, depending on the initial composition, and depending on the Damkohler number, you can generate quite different density profiles of this thickening lithosphere. And that has implications then for whether crustal foundering is likely to take place, depending on what Damkohler number you think is relevant in that situation, and depending on how much free fluid is available to the system. But like I said, we're still dealing here with a sort of zero spatial dimension problem. So this is not partial differential equation land yet. So I'd like to move on to a sort of simple example where we do get to use FEniCS and you solve some partial differential equations with the example of saturation gradient chemical diffusion. And in this case, we have some experimental constraints on this, which were run by Ming Hao and Anne Pommier. And so saturation gradient chemical diffusion is a process that happens in experiments, and it's often seen as a problem in experiments because it causes samples to segregate, causes partially molten samples to segregate at high pressures. And they're segregating because the experimental apparatus has a temperature gradient across it that it's very hard to eliminate from the system. But it's useful to us because it gives us a sort of calibration and test for our reactive thermodynamic models in a sort of simple thermodynamic system. So what's happening here is that the melt, the partially molten rock, the melt is forming and it is assumed to be in equilibrium with the liquid on the liquidus of this four-stride silica system. But because there is a temperature gradient, that melt experiences gradients of chemical potential, which drives the components within the melt through diffusion to migrate and throws it out of equilibrium, which drives melting, this yellow layer at the top, at one end of the sample, and freezing at the other end of the sample. So we can see that this melt layer is growing with time, with duration of the experiment. And a little harder to see, but we can also see a pure four-stride layer segregating out of the system above the solidus in this layer here. And in these experiments, we can also constrain the temperature gradient that's driving this process because we have a Spinel thermometer on the outside of the molybdenum capsule. And that Spinel thermometer is giving us a proxy for our temperature gradient across these experiments. In terms of the numerical model, it is a one-dimensional numerical model So our geodynamical model here is just reaction diffusion. We're solving a series of conservation of mass equations, just like I showed before. And we're closing those mass equations by coupling it to our thermodynamic database. And in this study, we considered a couple of different thermodynamic databases implemented using Coder and ThermoCodegen. So the Houdon et al. Database, which is shown in sort of turquoise here. And we also calibrated a version of the Holland and Powell endmembers and a solution model to fit the Houdon et al. Model. And so Houdon here is using a quasi-chemical solution model for their melt, and Holland and Powell are using a enstatite speciation model for their melt solution. And what we're taking from this database are those chemical potentials, because our diffusive fluxes are related to gradients in the chemical potential. And as I mentioned earlier, our mass transfer terms are also related to those chemical potentials. And what that model ends up looking like, here we have a sort of zoom in on the liquidus of the phase diagram. And on the right, we have the phase mass fractions of the different phases in this system. And we can see if we run that forward in time, what we see is the melt layer growing at the top of the simulation and that forced-right layer growing from the base of the simulation. And just like in Mitchell's example, we have a Damkohler number that's controlling the relative rate here of reaction to diffusive transport. And if we modify that and run those simulations again, what you can see is that that is controlling how diffuse or how smeared out these reaction fronts are between these phases. But we saw in the experiments that we have quite a sharp contrast between our melt layer and our forced-right layer. So we believe the Damkohler number here is quite high. And so we can calibrate our time scale of our simulations and compare it to our experimental data at different temperatures, and use that to fit the experimental data with our numerical model. And we do that quite well for the melt layer, which is the layer that has this sharp interface between the melt and the solid. But you can see here for the olivine layer that's growing from the base, we don't do a very good job with these models. And one possible way of squaring that circle is to have different rates of reactions, so different disequilibrium rates of reactions for the melting and the crystallization. And if we slow down our crystallization but keep the melting rate the same, we can still fit our melting data, but we can slow down and smear out the initiation of that forced-right layer in our numerical models. And what that looks like in the numerical model is that on the left, you have an example just where the reaction rates are the same for the forward and back reaction. And on the right, you have an example where we've slowed down that reaction rate of crystallization. And if I just play that again, you'll see that we still maintain this sharp interface for the melt, but our forced-right layer grows more slowly. And we see disequilibrium effects with the composition of the melt leaving the liquidus composition. So I wanted to just end by saying why I didn't talk about terra firma. So this talk was originally slated or titled Terra Firma plus ENKI. And for those of you who don't know, terra firma is a finite element model assembler. It's built on FEniCS and the numerical linear algebra library PETSI. And so it retains the flexibility that I was talking about earlier, but it provides a schema-validated option system on top of that. But the reason I'm not using it here or demonstrating it here is it currently uses FEniCS 2019, which has some issues evaluating large high-rank coefficients. And our thermodynamic coefficients in our geodynamic model here involve, derivatives with respect to every component of every phase. So they're high-rank coefficients, they're quite large. And so that meant that these sorts of problems weren't tractable with that version of FEniCS. Terra firma also assumes a two-level time-stepping discretization, which isn't always appropriate for these reactive transport problems where you have very different timescales between the reactions and the transport. So we've been exploring coupling ThermoCodegen with FEniCS-X, which is the latest FEniCS implementation, and with a different API to FEniCS 2019, and that includes fixes for those high rank coefficients. And we're using PETSI's time stepping interface, PETSI-TS, to allow us access to some of these implicit, explicit, strong stability preserving schemes that they're not so important for the examples I showed today, but we're also looking at advection reaction problems in our geodynamic models, and they become particularly important when considering the boundedness of our solutions in the geodynamic problems there. So I think I've used my time, so I'll skip over my conclusions and just leave you with the ENKI website and point out that you can reach out to Aaron Wolf from that website to get added to the ENKI chat and also to attend the weekly ENKI office hours if you're interested in getting involved and learning more about ENKI. So thank you very much.